Our topic here is integration, antiderivatives with e to the x. Well, we know the derivative of e to the x is e to the x. So by the fundamental theorem, we know the antiderivative of e to the x is e to the x. Almost. What's missing? Plus the constant. So up to the constant of integration, the antiderivative is e to the x plus the constant of integration. So we can use this in various forms. And this gets used in all sorts of computations. If you have any hopes of going through differential equations, you'll be doing e to the x with integrals all over the place. And so I'm going to just rummage through a few examples of this using this notion. You'll get things like this. This is 2x squared e raised to the power of, let's say, x to the third plus 1. Now, we have seen that if you have sine of an expression, very often you let u equal that expression. Well, another typical rule of thumb is this. If you have e raised to some power of an expression, very often, and notice this is degree 3, this is degree 2, that also should be an indicator. Very often if we have e raised to some power, then very often what we will do is let u equal that expression. That doesn't guarantee that will always work, but that's one technique to attempt, particularly at this early stage of the game. And so, we're going to let u equal the expression. This is x to the third plus 1. We need to find the derivatives of both sides. So the derivative with respect to u is 3x to the second, derivative with respect to x. But we have 3, we don't want 3, we want 2. And so we need to get rid of the 3. Again, you can, sometimes early on especially, I like to do with 2 steps. First, get rid of the 3. So you have a nice clean slate. And now create the 2 that you do want, because you can multiply both sides of this expression by 2. Yes, you could just do this with one shot, multiply by 2/3, but by hook or by crook, I think we should be able to get to here, and the substitution is exact. Because e to the x to the third plus 1, that becomes e raised to the u. We're translating into the u language. The leftover bits are 2x squared dx. That translates as 2/3 du. And so the substitution is exact, and so we should be able to write this. E to the garbage becomes e to the u. 2x squared dx becomes 2/3. Let's just throw the constant multiplier out front and let the constant multiplier multiply along. Because the antiderivative of e to the u du is e to the u, and then we throw on the constant of integration. And then the last thing is go back to the original variable using the let statement. So this is 2/3 e raised to the power x to the third plus 1, and we're out. One thing you could do, if you wanted to, you could take the derivative of this expression, and sure enough, if you did that, you would get precisely that value. You can always check your antiderivatives by finding the derivative to make sure you get back to the original integrand. So this is a very common occurrence here, very commonplace. Let's throw in another little twist here. And I want to make it look sort of like, let's go e raised to the power square root of x minus 1 over the square root of x. And this looks like a mess. But we don't want to use radicals. Radicals don't play well with the calculus. They don't play well with derivatives. They don't play well with antiderivatives. So I'm going to rewrite. I'm I'm going to rewrite this as e raised to the power x to the 1/2 minus 1 all over x to the 1/2 dx. Let's see what we get out of this. Let's let u equal x to the 1/2 minus 1. Whatever e is raised to, let that exponent be the value for u. du, this implies du is equal to 1/2 x to the negative 1/2 dx. Is that what we have? Well, sort of. We just need to rewrite this. I need to rewrite this again because I want this to be x to the negative 1/2, and that's almost what I have here. So I'm going to rewrite this to make it official. This is x to the negative 1/2, e raised to the x to the 1/2 minus 1. And now my u substitution is almost right there, because this accounts for e to the exponent, and then this is almost what I have left. I just need to get rid of this 1/2. I know how to get rid of 1/2. Multiply both sides of this by 2. And that is precisely what's left over. The substitution is exact. And so when we substitute the x to the negative 1/2 dx, that translates as 2 du. I'm going to throw the constant multiplier out front. And then e raised to the garbage is e raised to the u. That is this is about as basic a basic form as you can get. The antiderivative of e to the u is e to the u, and there's my constant. And then finally, go back to the original variable from the let statement. So this becomes 2e raised to the power x to the 1/2 minus 1 plus the constant of integration, and we're out. So, e raised to some expression. Very often, the tool you will use is let u equal that expression, and then whatever is left over, you can manipulate it so that it looks like you want it to look, to make sure that you've accounted for everything in this u substitution. So integration with e to the x is a straightforward procedure. Very often what you'll use is let u equal the exponent, particularly if that's a larger expression. One thing to bear in mind, and I'll just leave with this, if you have e to the 4x, that is the same thing as e to the x to the 4th. If I have e to the 2x, that's the same thing as e to the x squared, because that's just the properties of exponents. When you raise a power to a power, you multiply. And so one thing you can do here, e to the 4x, sometimes this gets used. This is e to the 2 times 2x, which means this is e to the 2x squared. So very often, e to the 4x gets rewritten in this form. Sometimes it gets rewritten in this form. E to the 2x almost always needs to be rewritten in that form. So which one of these do you use? Well, you play with your problem, look at what you generate, and you're aware that you can rewrite some of these expressions in other forms, and that will assist you in matching up the leftover pieces from the values in the u substitution.